Welcome again. So yesterday we saw these very basic algorithms, right, for binary field arithmetic, and I gave a background on binary curves. So today I will throw half of that in the trash and replace with something faster and more secure. That's the whole point. And we finish on this, right? The implementation security is important, so you shouldn't, all those time-space trade-offs we saw, for example, yes, they are not a great idea because they might randomly index vectors, and this can leak information, right, about secrets. So we find ways today of making this more secure, although we're using some of the ideas. So yeah, we talked about this. So I applied those ideas to one particular choice of parameters of fields and curve, and finish with also making this scalar multiplication more secure and using some nice tricks to compress table sizes and things like that, and with a couple of notes on lattices. So to kind of rehash the motivation, binary curves were proposed right in the beginning, as I was saying yesterday, but they were quite inefficient, especially in software, right? We didn't have the instructions or the native support to make them competitive, but after Intel introduced binary field multiplier, a carryless multiplier in 2010, this suddenly changed the trade-offs quite a bit. And this instruction was initially, the instruction I'm talking about is CLMU, right? It's right there. It was initially introduced just to accelerate the GCM mode in AES, and it cost 14 cycles. And it's funny that the same CPU can multiply 64-bit integers in like 3 cycles. Why would the carryless multiplier, which is like a multiplier without the carry logic, be 5 times more expensive, right? It's just trade-offs. No one benchmarks AES GCM. Everyone benchmarks integer multiplication. So it gets, AES GCM doesn't appear in the Intel commercials, so no one cares. But then they started carrying, and now you can compute 2 of these per cycle. So they actually, since Haswell, it became really, really, really fast. ARM tagged along, and initially they had introduced a vmul.p instruction that does 8 simultaneous 8-bit multiplications, which is useful but not great. And later, a pmul instruction that's actually not for packet, is obviously for polynomial multiplication. That's where the p comes from. And the second L there is for long, because it's a 64-bit value. These were the technological side. We got much better instructions, but also things changed or moved on in the algorithmic side. So there is this nice paper in 2009 by Galbraith, Lee, and Scott, where they actually construct a class of curves that have efficient endomorphisms, and we'll talk about what this means over some quadratic field extension. And that idea was extended to binary curves the same year, although they didn't have a competitive implementation yet. That took a couple more years to be developed. But then we were in this case where, oh, now we have all the ingredients to have record-setting binary curve in terms of performance. So now I'll talk about this particular implementation layer by layer, right? We start with the base field, we move to the quadratic extension, to the formulas that I'll show them. I won't derive them, of course, and then scalar multiplication at the top. So let's start with the base field. So I'm doing the same thing I was doing yesterday. I'm picking some field FQ. In this case, it's 2 to the n, right? For m equals 127, with a particular choice of polynomial f that's a trinomial. It's to allow fast reduction. I'll have this on the bottom of the slide. But because I want this particular choice of curve later on, that we have some efficient map, just like the tau map for Koblitz curves, it will be defined over FQ squared then. That I'm also defining using some irreducible polynomial over FQ. And then I will represent both as in polynomial basis. So the base field is represented like that. Observe that I change from z to x, just to make a difference between the abstract and the concrete. And then for the FQ square elements, I'm using some root u to define, so quadratic non-residue to define the extension. How to pick those? So I need something to the order of 256 bits for the order of the curve to be 256 bits too, to have 128-bit security, right? As we discussed yesterday. So I'm picking the base field to have that format, and observe that this is a sparse polynomial, and the numbers are quite suspect already, right? I'm picking things close to powers of 2 because this will allow me to shift faster later on. And I picked the simplest irreducible polynomial for the quadratic extension there to also be to also reduce fast if needed or when needed. So we talked about squaring, and that will be the first instruction we actually use this for squaring in square root. So yesterday I showed how to do squaring with a table, and I explained that we could do square root with tables too by just using tables to split the odd and even bits. So for a high-speed implementation, and you want it to be again secure, you don't want time-space trade-offs, right? You don't want pre-computed tables that can leak which positions are being queried. So one nice trick we found on this work was how to repurpose this instruction. Is what I call instruction bribing, right? Instruction does one thing, you give a bribe, it does something else magically. So I'm Brazilian, that's how we think about things. So this instruction takes two inputs. One is a source register, this is a vector register, so it's 16 bytes, right? It's a 128-bit register. And there is a mask. So what this instruction basically does is it copies bytes from the source to the result according to the mask. So if you look at the operand here, the mask, we have 3 0 bytes. So it takes the 4 less significant bits of each of these bytes, uses it to index the source, and copies this to the results. So because we have 3 0 indexes here, the instruction would take the byte with position 0 and copy this to the result, to the output register. So it's a byte shuffling instruction, right? It does it for all the 16 bytes. Of course, there is a hidden power here. What this instruction is doing is parallel table lookups. So if you have in source some function that takes an input 4 bits and produces 8 bits of output, right? And you have all the f of I for I from 0 to 15 on the source register, you just put the indexes on the mask register, and then you evaluate this function in parallel 16 times. So then we can turn this instruction from a byte shuffling to actually a table lookup instruction, right? It's just convincing it can do something different. So that's exactly what we do. This is the function we are evaluating. We're picking 4 bits of input and just expanding it to 8 bits. And graphically looks like this, right? So we have all the possible 16 values here encoded as bytes. These are the outputs of the function. And the index is here, the 4 less significant bits of each byte. And then we can compute the squaring of 128 bits efficiently. That's one classical trick of crypto engineering, repurposing instructions. So this was squaring. How can we do multiplication, right? So I told you that the base field now has 127-bit elements. These are polynomials, right, of degree up to 126. They are represented in 2 64-bit words. So now you saw the Lopez-Dahab algorithm, the shifted addition version. That's bad again, because again, time-space trade-offs, right? We have a table there that we scan, that's not good. But if we have a native instruction that multiplies 2 64-bit words, then we can use the careless multiplier. How do we do this efficiently? Karatsuba, the divide and conquer strategy for multiplication. So we write A and B as in this way, right? Of course, A here is this combination of the 2 packet 64-bit values. B is the same. If we distribute this naively, we have 4 multiplications to evaluate, right? 4 careless multipliers between 64-bit values. But with Karatsuba, we can actually break this into 3, and you can see the 3 multiplications here, right? This is the one, the blue one, the orange one, and the green one. So it's 3 multiplications plus some additions. What is great about Karatsuba over binary fields is the same idea you probably saw for integers, is that we have this value in the middle, right? That's multiplied by x to the 64, so it changes values in the middle. In binary fields, because we have no carries, this actually simplifies because you do not have to add and then propagate the carry to the top. So you just XOR this second or this intermediate result in the middle, and then it's done. Just 3 64-bit multiplications. If you count that you can issue 2 per cycle, this runs extremely fast. Okay, if we multiply, we get larger degree, right? Is that a question?
Yeah. So you said you could do 2 per cycle.
Mm-hmm.
Does it?
That's peak performance, right? They cannot depend on each other, but that's the maximum throughput.
But when you go from 4 to 3, it's still 2 cycles.
Yeah, the difference is, so you can issue, to be precise, I can compute 2 per cycle, I can issue 2 per cycle, I can initiate. but the results will be ready longer. So you still need to carefully schedule to be able to enjoy those results. That's why when you look at the multiplication, the cycle constant multiplication, it won't be like 5 or 10. It will be 42 because you still lose stuff. But that's top performance. You can issue 2 per cycles. 2 per cycle. Other questions? At least that's what Intel says. And it kind of matches what you can empirically test. So if you multiply, you now have a double degree polynomial, right? That's the result of multiplication or squaring. You need to reduce. We picked F to be suspiciously well-structured. How can we reduce? So if you look at the result of the multiplication on the base field, you have something with 254 bits, right? So we can split in 64-bit words like this, and then we need to reduce. And then you formulate modular reduction by looking at what you can do to process bits in parallel. So I want to reduce this, of course, to 128 or 127 bit result again. That lies in the base field. But then I can look at, if I reduce this single bit, and if I look from, I reduce x to the 192 modulo f, I see that reducing this single bit actually implies adding a bit to this position, right? So we do the same here. Instead of doing this bit by bit, we pick the whole word, and then we add to those positions, because this will be valid for the whole word, all the top bits in yellow there. This means that I need to pick this top word and add it to the position 128, the position 65, which means shifting it 1 position to the left before you add. One thing that's great is because the field is a bit smaller than 128, is that this shifting here this will be a 0 bit, so we don't need to deal with it. If I continue doing that, now I need to look at the 128 bit position, and then again, from the shape of F, this means that I need to add that word positions 64 and 1. So I do the same, but now I need to deal with the pesky bit there as I shift to the left by 1 position and add it to the position 64. After this is done, I have something that's almost reduced. There's 1 bit at the top that's left unreduced, right? That you can handle by, again, looking at the shape of F. Later on, we figure out that we didn't need to reduce this bit. There will be some numbers that show this afterwards. So reduction in this case, we managed to perform with 11 instructions. This is the XORs and this is the shifts. To do this, we also figure out that because squaring has additional structure, you went adding 0 bits. You don't need to add those if they will be always 0, right? Which is the case of the pesky bit I had at the end that I need to add shifted versions of it because I know it will be always 0. So then for squaring, we can do this with just 6 instructions. At the end, we figure out, oh, reducing modulo f strictly is silly. We should actually reduce times x times f. There shouldn't be z there. X times f, and then leave results unreduced with just 128 bits. We reduce them at the very, very end. So this is a redundant representation we introduced. Because reducing that single bit is expensive and doesn't give you anything back, right? You can always leave it unreduced at the top. Yeah.
So when you choose f, so you choose it to be like close to some word size, essentially.
Yeah.
So if you look at we talked yesterday about P256, they do the same thing.
Yeah.
But the curve 25519, they choose like 1 big and otherwise small. Did you check the performance here as well? Like if you do x to the 127 and then you do plus, x to the 8 instead of 63 or something like that.
Yeah, what's more important here is actually, if you think about it, is the differences between the powers to be a multiple of the order, because that's what determines what the shift amounts will be. If I have 127 plus x to the 8, let's say, then the difference will be 120. Then I will have to shift something that's not the multiple of the order. That might be a bit, for some of the shifts, that would be more expensive. That's what NIST also got wrong with their primes in NIST, because you have all these pesky low significant bits, and the differences are not aligned with the words. That's why it looks uglier than this when you reduce modulo the NIST primes. Yeah. Other questions?
You mentioned this polynomial suspiciously regular, or is it really irreducible polynomial?
Yeah, yeah. You can test in Sage with 3 lines. If I remember how to do that, I would do it right away. But, but it's irreducible, yeah. Yeah. Of course, x times f is not reducible anymore, right? It's divisible by x, obviously. But you can still manage to do arithmetic properly. You only reduce at the end. If you need to invert, of course, then you need to be careful because you need to fully invert before, otherwise it could be not coprime with x times f, and then you have problems, right? There could be maybe implementation security issues when you need to invert. But we always fully reduce before inverting. Other questions? Okay, base field is done. Let's go to FQ square. So again, I define a reducible polynomial G, right? A U square plus U plus 1, because U plus 1 is not quadratic residue. So I can do that. And then I'll quickly go through the operations, right? So now we have multiplication again, but those elements there will be FQ square elements, right? I'm writing them as, of course, polynomials on the variable U now, on the extension field. So I multiply them together. Again, the naive solution would give 4 base field multiplications. We use Karatsubo again, 3 field multiplications. And we don't even need to shift, right? Because it aligns quite well. Squaring is great because, again, you have freshman dream. You just distribute squaring across the whole thing. So we don't need, we compute the squaring the extension field essentially with just 2 squarings in the base field, right? This and this, and 1 addition. So it's quite efficient. Square root, if needed, we don't. You can also do the same. Just if you have square root over the base field, you just distribute. And inversion, it's simple too. You invert on the quadratic extension by being able to invert on the base field. But I won't explain why this formula works. It's a simple linear algebra thing, but I don't have enough slides. But it's 1 inversion in the base field plus multiplication, so it's quite fast, and squarings too. So this is the outcome of this. If you have the base field implemented, you can implement the quadratic extension with for multiplication with 3 multiplications, the base field plus additions. For square root, it's just square roots again. Squaring is just 2 squarings. And for inversion, 1 inversion in the base field plus some other operations. Of course, the inversion in the base field, you dominate there because that's too expensive. So now to get a sense of how these things look like, these are old timers. It's from Sandy Bridge. It's a machine that was just before Haswell, so multiply wasn't too fast there. I think it was 3 or 4 cycles. But I think they illustrate the trade-offs better. If you look at the tabulated real recent CPUs, the multiplication square and square root will be too close, and then it's not that interesting to look at. So on the first 2 columns there, you have base field, and on the quadratic extension there, you have, of course, the extension field. And then you can see that what dominates in terms of what's needed for the group law evaluation is multiplication, right? Multiplication is non-trivially more expensive than addition is not even there because it's just XOR. You can do maybe 1 or 2 cycles, but multiplication is the expensive part, right? Squarings are quite efficient, just 9 cycles here. Inversion is way less efficient, but we've used projective coordinates, as we talked about yesterday, to just delay inversions until the very end. If you look at the timings for the base field and the extension field, they won't match exactly the previous table. For example, 1 multiplication on the quadratic extension, you would expect to be the cost of 3 multiplications on the base field due to Karatsubo, right? But it's less than that because, well, scheduling issues, CPUs are not as deterministic as you would expect. So it's not the same. Both compiler is scheduling and also instruction execution is scheduling. So the hardware is a bit less deterministic than you would, predictable is the right word, than you would expect. Good. Now we have extension field of the correct size, so we can put a curve on top, right? That's what we wanted to do in the first place. So yesterday we talked about this Weierstrass curve over some field, in this case is FQ square. And then this is the form for binary curves, right? And then one thing we introduced in a paper in 2013 was a new coordinate system. So remember that they showed you the the formulas for the affine group law, where I always computed the slope of the line passing through the points, and then from that I would compute the point doubling or the point addition of 2 points, right? What we figure out is, if you already, that's not super brilliant to figure out, as you can expect. If you already know the slope, then it's very efficient to derive the coordinates of the resulting points. But knowing the slope is expensive because you compute an inversion, right? And then we thought, why don't we represent points instead of x and y by x and the slope of the line tangent to that point on the curve? So then a point now is represented by x and lambda, where lambda is this tangent of the slope at that point. By picking this Weierstrass law or Weierstrass equation and plugging in or rearranging the curve equation to use lambda instead, then we get this affine lambda equation now, on lambda affine coordinates, if you will. That still looks quite okay. And you can make it projective too by just, at least the most efficient projective space we found for this model was the homogeneous one. So we weight the 2 coordinates by z, and then by just plugging this x over z and L over z for x and lambda there, we get the projective version of the curve equation. So that's the model we were looking at, or we'll be working on later. And in 2013, we showed that point addition was and point doubling were slightly faster in this curve model than the Lopez-Dahab model that was the projective space that was most efficient before. So now points will be represented as x, L, and z projective space, right? So the x over z and L over z if you want to convert to affine. Make sense? So how to derive formulas? I won't derive all of them, I'll just show them. How can you obtain like point doubling formula? You pick the affine point doubling formula, you plug in the new coordinate system, you derive, you optimize the formula, you get something like this. So it's point doubling in projective space. And of course, this might look like it's really easy. You just can then invent any coordinate system and then plug in different weights for the projective coordinates, for example, and then you get a faster point doubling formula. The problem is that that's what we try to optimize the formulas, right? We try different projective weightings, and then we figure out most of them are less efficient than the best in the literature because people have tried this before. But surprisingly, we were lucky that this was faster. So, with this point doubling formula, we need just 4 multiplications, 1 multiplication by the A coefficient of the curve that's here, and 4 squarings. We also figured out back then in 2013 that there were 2 different ways of computing the L, the lambda in projective coordinates. For the point doubling, there is a different formula that looks scarier, but it's actually faster. It only requires, if you replace this one with this one, it goes down to just 3 multiplications, because we're trading off 1 full multiplication in the field by multiplications by the curve coefficients, which are chosen to be small. So it's, again, the dangerous game of searching parameters. You pick the curve to be very, very special, not only having an additional structure, but also having small coefficients, because you can use those to accelerate the implementation of the arithmetic. But you're making your instance more and more special of the hard problem. So this is the formula for point addition. You do the same, right? You start with the affine formula for point addition, plug in the coordinate systems, you expand horribly, you optimize, and you get something like this. Then we can do a point addition, 11 multiplications, and 2 squares. I'll have a slide comparing this to the previous work shortly. One thing that's interesting too is there is a case that arises in practice, which is mixed point addition. If you remember double and add, we always double the accumulator, but we add p to the accumulator, right? P comes in affine coordinates as you would expect. So p remains in affine coordinates through the whole algorithm. So you're adding a accumulator q in projective coordinates to a p in affine coordinates. So you know that for p, z will be 1, so this can be optimized. In this particular case, all of this, if you're adding q in affine coordinates there, all of this would just go away, these multiplications by zq, because it's 1. We call this mixed addition, and then it causes 8 multiplications. That's something also that all elliptic curve implementations do to enjoy faster mixed additions. And I think I'll just skip this. It's just another ugly formula. Comparison. So Lopez Dahab was the dominating coordinate system that was the best before, and Lambda was our paper in 2013, and this is the difference. So for full point addition, we save 2 full multiplications. For mixed addition, we save squarings. For point doubling, we have this trade-off in one formula. The other formula, we save 1 squaring. And also we have a formula that to double and add a point, that we have a specialized formula that saves a multiplication in 4 squarings. So we saved in the whole curve arithmetic multiple operations, right? The ones that matter more, of course, here are the multiplications. The squarings do not matter that much. So what really made a difference in practice here was exploiting this formula and these 3 squarings here too, because, well, 3 squarings are almost 1 multiplication. And for this, we won the best paper award at Chess, because no one had used this coordinate systems in almost 20 years.
Theo?
Yep.
And do you also have complete formulas?
We'll get back to that, but no. The quick answer is no. And then we cheat to be able to use incomplete formulas. So what Jehan is asking here is, and maybe to connect to Danilo's question yesterday, in prime curves, it's discussed a lot the idea of having formulas that can handle any corner cases. So if you want to add, for example, a point at infinity and p, or you want to add p and minus p, the formulas won't produce wrong results. In the Weierstrass model, the formulas produce wrong results. So you need to test that this is actually the case. You cannot use the point addition formula to add a point to itself. You need to use a point doubling formula to that, right? So in the Weierstrass case, we have a branch saying, oh, are you adding the point to itself? Then use a point doubling formula. Otherwise, just continue executing. And then, up to recently, that's the best you could do in Weierstrass, but this is bad from implementation security because now you have branches, right? So the Edwards formula, the Edwards model and the Montgomery model allow you to do this without branches. They have complete formulas or almost complete formulas. This model in particular doesn't have complete formulas, but we formulated the scalar multiplication algorithm in a way that we can prove that we never hit those corner cases. So we are cheating really badly, yeah. And they are now complete formulas for Weierstrass, but they are 30% slower, the Costello-Battina formulas. So I talked a lot about having efficient endomorphisms and this GLS family of curves. So just quickly go through this. So the authors GLS, right, they propose this family of curves over FQ square such that you have an efficient map. So you have an endomorphism psi here that takes a point in the curve and maps to another point in the curve. And what the action of this map actually does is multiplying by some mi that you can just compute by taking the square root of -1 modulo the group order. So this should be a large prime that defines the group order. If you can do that, you can actually break scalar multiplication, the full scalar multiplication, into 2 smaller ones. So if you can pick a curve that has this map psi here, and you can convert k into k0 plus k1 times mi, where k0 and k1 are half of the size of k, right? You have a recoding or decomposition algorithm to do that. Then you can compute scalar multiplication like this, where you have, instead of a full large scalar multiplication, you have 2 smaller ones because these 2 integers are half the size of k, assuming also that this map is efficient to apply, right? Of course, psi shouldn't be, I don't know, as expensive as the scalar multiplication, otherwise what's the point? And then if you can do this, you can then run these 2 scalar multiplications together. We call it interleaving, and you save all the point doublings. It's the same idea as multi-exponentiation. You have seen that before, where you share the squarings. And I'll have a slide showing this, probably the next slide. So scalar multiplication law, let's go back to the double and add algorithm and look at it from a side channel or implementation security perspective, right? And then we refine this multiple times until we get something secure at the end. So again, we have P in affine coordinates, that's an input. We have the binary expansion of the scalar, and then we scan this from the top to bottom, always doubling the accumulator. In this case, I called it R, and then doing a point addition when the bit is 1. obviously, as we talked about, there are multiple problems here, right? One is the loop runs for as many bits k has. That's not good because it leaks how long k has. K will be, in average, at most 1 bit off the group order, but we don't want that. We want it to be regular, right? We don't want to leak anything about k. But the big problem there is the branch. So if the adversary can figure out if branches are being taken or not, or the adversary can figure out when the point P is being read in memory using a cache timing attack, as we talked about the flush and reload attack, the adversary can figure out when the branch is taken and which bits of the key are won. Maybe this won't be super precise and some bits might be wrong. Adversary can find a way to fix the wrong bits as well, as long as the rate is not too high. How can we protect this? We need to fix the number of iterations somehow. We need to remove that branch. We need to implement point addition in constant time using, in the conventional solution, complete formula without branches too, right? So you need to pick the coordinate system carefully. So if you're implementing prime curves, use the Edwards model, for example. Let's fix this. First fix is, okay, I won't deal with the number of iterations yet, but I can fix the problem with the branch, that's the biggest one, by using a conditional copy. So I always compute the point addition, and if the bit of the key is 1, I overwrite the accumulator with the result. Otherwise, I don't do that. Of course, you need some, ideally, some instruction that does this, a conditional copy instruction, in which depending on the value of a bit, it copies or doesn't copy a certain value, assuming that it still spends the time a copy would spend, right? Otherwise, you're back to square zero. So this works and relies on the compiler also not messing it up. So if you pick, for example, the Clang compiler, it has a pass at the end that it looks at conditional copies and say, oh, stupid programmers, they're doing conditional copies. These should be branches. So it reverts and reintroduces the branches and removes the sidechain of countermeasures. So LLVM is really nasty at doing this. But of course, when you compile crypto code, you remember to disable that pass. Yes?
And there's no conditional copy predictor or anything like that?
Not that we have found yet.
Okay.
I wouldn't be surprised, right? There are predictors for everything.
Yes.
But we haven't found that, at least on Intel. For smaller microcontrollers, people have used template attacks to figure out, because, well, if the condition is met or not, there will be bits on the CPU that will be turned on or not to indicate the copy to be made or not. So this leaks certainly through the power side channel, because there will be bits turned on.
Yeah.
If you can detect that in microcontrollers, that's easy. You can actually figure out if the copy is being done. But here we're talking about only constant time. We're not taking into account power yet. There are other ways to do that. Good question. Other questions? If you don't have a conditional copy instruction, you can also do this with Boolean operations. And again, hope that the compiler doesn't mess everything, but sometimes it does. So the problem here, of course, is instead of computing or paying the cost of a point addition in half of the iterations as we had before, now we pay it at every iteration, right? So this is slower. This is quite slower. You remember that point addition is much worse than point doubling. So we're making this almost 2 times slower. That's not great. Can we do better? Yes, in some cases. So one way to refactor this idea into something more efficient is the Montgomery ladder. You might have heard about it multiple times before, especially if you read the Curve 25519 paper. So it's a scale multiplication algorithm that by design it's more regular. So how does it work? It has 2 accumulators there, initialized as P and 2 times P. And again, it scans the bits of the key from top to bottom. And that independently of the bit that's being, the bit of the scalar or of the secret key here, we always do 1 point addition and 1 point doubling. The inputs and outputs of these operations are different, but then you use these conditional copies to actually make them always the same, or at least the same positions in memory. You copy the inputs conditionally to certain registers, you operate over the points there, you do conditional copies to write back the results. You can also do a conditional swap to do it more efficiently. And this doesn't look very different from the algorithm I had before, right? per iteration, I'm doing 1 point doubling and 1 point addition. That's exactly what I had. What do I mean by this being more efficient? Well, in some curve models, like Montgomery and Edwards, you can actually do a double and a point addition involving the same points in a faster way. For the curve 25519 formula or curve in particular, Montgomery curves in particular, you can do this with only the x coordinate. You don't need the y coordinate. So these formulas are faster, which is not really possible on the, or at least doesn't work that well on the previous slide. So we're making progress. Here we still have a problem with the number of iterations. You can figure out the branches using conditional swaps, but you still need to implement the group law in constant time. Otherwise, the adversary might be able to distinguish one case or the other. So that's a refactored version of the algorithm. Now we're dealing with the number of iterations. How can I fix the number of iterations? I conditionally add R, which is the group order, or 2 times R to the scalar, such that the result of the addition is fixed length. So now I know that all scalars will be fixed length, right? So now I can formulate scalar multiplication or run scalar multiplication depending on how many bits the order of the group has instead of the specific scalar k. I do this conditional swap to swap R0 and R1 depending on the bit of the key, and then I do the point addition and point doubling, always using the same inputs, right? And then I fix the swapping I had before in constant time too, before I finish this iteration. So that's essentially what curve 25519 does, but only using x coordinates because of the Montgomery curve model. So then I fix most of the problems here. Yeah, exactly. It uses the x coordinate, but in projective space to not pay inversions. So I fix most of the problems. We're quite happy about this so far. Questions? Does this still make sense? I hope this is a yes. What can go wrong? Well, if we look at OpenSSL code, they had one very interesting case of timing difference in the first iteration of the loop, which was the following. First, they implemented the Montgomery ladder over Weierstrass, so we wasn't over a complete addition formula case. But notice that the first iteration is quite sensitive here. We initialize these two scalars, or these two accumulators, sorry, with P and 2 times P, right? But look that if the adversary can figure out that which accumulator is being doubled here, is it the original R0 or the original R1, depending on the swap, right? Then he can figure out what if the accumulators were swapped or not, and this leaks a bit. So in the OpenSSL code, if you look at it, R0 is initialized with P, affine coordinates. R1 is 2 times P, projective coordinates. So if you could figure out if this is a projective point doubling or an affine point doubling, with the input coordinates being an affine point, then you figure out the top bit of the scalar, of the key, right? In this case of K. And that's the ladder lake attacks, the CCS paper from 2020, where we managed to exploit the single bit leakage over many nonces in the ECDSA signature to recover the whole secret key, the whole signing key, just 1 bit. Akiga wrote less than 1 bit because the attack is probabilistic, so we're not 100% sure and figure out that bit. It's close to 1, but it's less than 1, right? So we're being cheesy, I guess. It's like probability of success times 1 bit. Okay, but we still have a problem here in this algorithm. If you don't have a nice elliptic curve model where doing point doubles and point additions together really fast, or can compress just to x coordinates, you still pay the price of essentially 1 point addition per iteration. Not great. Let's make this better. How can we make this better? So now we're assuming that, again, we have the endomorphism that allows us to write K as these two subscalars K0 and K1, right? That we will use one algorithm to multiply these two together. So now we're recoding K0 and K1 in some place where we make the point addition iterations deterministic. So we recode them using a fixed length expansion, always gives the same expansion in terms of length, by Joa and Tunstall, in which you have an expansion of fixed size again, where the positions are, the non-zero positions are known in advance. This expansion always gives you positions, non-zero positions that are W spaces apart, W zeros apart. And this is great because then you can run something similar to double and add, and you know when you add. So you don't need a branch for that. If you have W minus 1, in this case, zeros, you just do point doublings here, 1 point addition. A sequence of point doublings, 1 point addition, and so on. Right? So you transform one problem into another problem. But the problem here is these digits will be in some set. So it will be signed and in some set, which means that instead of adding P, the scale multiplication algorithm, you might have to add 3 times P or 5 times P or 7 times P. How do you solve that? Without having to compute 5 times P, add that to the accumulator. And maybe in the next iteration, you need 5 times P again, and you multiply it again, add it to accumulator. How can you solve that? You pre-compute the table of the small multiples of P. What's the problem with that?
Cache.
Cache. If you can pre-compute the table, but you can just go to the table and read it directly. So you need to solve that other problem. Notice that each solution here like opens another problem. That's what we do. So this is the resulting algorithm at the end. We compute this, we pre-compute this table T with all these multiples of P in that digit set, right? Using the same curve arithmetic formulas I showed you before. And then we have recoded K into K0 and K1, and in particular K0 and K1 in these fixed non-zero position expansions that have fixed length as well. So we can fix the number of iterations to the fixed length of K0 and K1, and then do a sequence of point doublings that is known in advance again, and then read Q and S from the table, and then add them together, considering that one of them will be from K1, so the endomorphism needs to be applied before the point addition. These reads here need to be careful. They can't just go to the table and immediately read the position there. They actually need to scan the whole table and read one position while keeping that position secret. So you use the conditional copy instruction again. So you scan the whole table, pick the position you want, write this on Q, do the same for S, and then you do the point additions at the end.
Why would a conditional copy read the data from the memory?
So if the conditional copy is implemented correctly, it should read from memory and discard the result when writing to registers if the bit is not set.
Oh, right, I see.
And then we cross our fingers that Intel didn't completely mess up. Yeah.
Okay.
Yeah. You can also do this again with Boolean operations, and then you hope that the compiler doesn't mess up.
Is this conditional copy, is this an instruction added just for crypto people, or?
No, it was there before. It's used for semaphores in operating systems. Remember, you need these atomic updates where you move 0, 1 to some variable or synchronizing threads and stuff. It was implemented for operating systems. We're just piggybacking on that. Yeah, it's there for a long, long time.
And so there's non-crypto applications.
Yeah. If you remember ARM v7, ARM was great because every instruction could be made conditional by this predication mechanism. So every instruction you could turn on or off for the instruction to be computed and throw the results away, to remove branches, because they didn't want branches to penalize the pipeline. So they added this on ARM v7 as a feature that if you have a short branch, you just predicate the instructions on that branch and remove the branch effectively, to not jump around in the code and make the execution pipeline predictable, so no stalls or flourishes. And then ARM v8, they said, yeah, who needs this? And they throw everything away. Yeah. But they had that. Yes.
Why would the OS people care about the bits being copied or not?
You mean if you want to implement a semaphore, you need atomic rights to copy one position to another.
Yes.
It was used there. That's what I meant. If you don't have atomic rights, then you have this problem of like time of check or time of use. How do you implement a semaphore? You check that the mutex is not taken, and then you update the mutex, and then another thread runs in between, and then two threads now have a mutex, stuff like that. So you need atomic copies. If I remember correctly, I'm speaking from underground operating system courses, like 20 years. Yeah.
It works.
But I remember it worked like that.
You have a single processor with the same.
Now you might have multiple threads, but they're sharing some mutex in memory, right? You want to
But if you have
only one
cores. Okay, but
then you have
mind.
multiple threads, but different threads per core, right? So you coordinate this per core. You don't have the threads competing.
Exactly. Okay. But
If you have multiple cores running multiple threads and they need to synchronize, then they use a length variable that you can still do this. Only one thread can have the mutex, right? And then you need atomic rights for that.
Right. Sorry.
We can look at Wikipedia again at the
Yeah, yes.
and remember if that's exactly what happens there. But that's what I remember. But we inherit the instruction from there. And it makes sense anyways to remove branches. So if the compiler will sometimes issue that instruction to remove small branches, as the ARM processor did by design, right, to avoid jumping around. So, so I think I can move. So one thing I did here is observe that now I'm doing two scalar multiplications together here. I'm sharing the accumulator for both multiplication by K0 and K1. So these doublings here are shared for the two subscalars, which means that this loop runs for less iterations than the one we had before. We effectively save half of the doublings. We're making a difference here. Okay, so now this is the latest trick that actually Marius had. Marius is my PhD student working on this together. He's Norwegian. He's in Canada presenting this paper 1 hour from now. So then he figured out the following thing. Oh, this seems like wasteful. We have two tables that are pre-computed here, right? And they have these small multiples of P, and we apply the endomorphism here. But there is some inefficiency here that we have like tables for the different points. Can we make this slightly better? That was the original question. So the core operation there is that, right? We double the accumulator, that was R in the previous slide, sorry, it should be R there. And then we add two positions in the table. One of them has the endomorphism applied, right? The one corresponding to K1. For some integers in that digit set, right? And then the idea is like, oh, maybe we do something different. Instead of having one table being used 2 times, that you scan the table 2 times to read the points, maybe we make a 2-dimensional table, where instead of having, again, one single table, we have a table with the 2 indexes here that we store this. And then we have one table that we can scan and already pick the added points. Instead of computing the 2-point additions here, let me point it to you. So we double, and then we add, and then we add again. Maybe we can compute these additions between the TIs and the TJs, store them in a table, and not having to compute them online. So we already do this in the pre-computation. But that's a stupid idea. Why? Memory is much worse now, right? Because now we have the size of the previous table is squared for all the positions, which means that if we scan the table, we scan a larger table, we're just making everything horrible. It's a quite stupid decision. So we have more points both to compute and to store, although we only do it once. But then we figure out a way to compress the table in which if you have a position ij, which encodes this, you can apply the negated endomorphism to compute the position j minus I. So you don't need to compute all choices of I and j for the table, all the tij's, you compute half of them, and you use the endomorphism to compute the other half. So it compresses it effectively by half. So now we can compute all these multiples, those were the multiples we needed, all these small multiples of p and j of the endomorphism, using point addition, the endomorphism to compute 1/2, and the negation to negate the points if you need, right? So we can pick all the positive and negative combinations of small I and j there. And this changes the algorithm. We have other stuff in the paper, I'll just skip that. So that changes the algorithm in the sense that now we do the same recoding, we do the same sequences of point doublings. Now we scan the table once to read the 2 points, and then we throw away, and then we figure out if we need to apply the endomorphism or not. This is the compression part. At the very end, when we read the point, we say, should we apply the endomorphism to kind of swap I and j by j minus I or not? So we handle all the cases there. Numbers, is this more efficient? So we implemented this on both ARM v8 and Intel, and I'm comparing against previous work using prime curves. So this is curve 25519, is the most efficient we could find online on ARM. This is the 4Q curve. 4Q is special because it has 2 endomorphisms. So it uses different ideas to decompose the scalar into 4 smaller subscalars. So it's a very special curve. This is the first line here is our work running on 64-bit ARM v8 using the previous algorithm that I had. Although with a new implementation of the finite field arithmetic that Marius has implemented. So that was our baseline. Pick whatever we had already, the best algorithm we had from 2016, implement on ARM. And then by making the table 2D, that's what the 2D means here, and reducing W, so we operate over smaller windows, otherwise the table grows too much, we still get a better latency at the end. And you can see that it's very delicate. If we again increase W to 4, which grows the table way too much, then we start losing. So this was the sweet spot we found. We also did operation counts in the paper to also show that it's not just an experimental empirical result. It also makes sense if you count all the operations. W equals 3 is what makes more sense because we grow in the table like by W square, but we use this compression trick. So there is a sweet spot somewhere that doesn't grow the table too much, and we still save enough point additions to make a difference. Yes?
How sensitive are these parameters that you use for optimization to, say, architecture or stuff like that?
What parameters that we change for optimization? Compiler version?
So the size of these tables, for example, does it matter what the architecture is, or if it's better to use that size? Or yeah.
Very good question. It matters somewhat. The trade-offs here we have, of course, the arithmetic density. So if, for example, reading from memory is too expensive on a certain CPU, this strategy will certainly be better than the other ones that have longer tables, right? Larger tables. If conditional copy is too expensive, which increases the size of just reading a point, the same applies. So you have a delicate balance between how large the table is, how efficient reading from the table is, doing a conditional copy from the table, and so on. And this matters a bit, or it makes a bit of a difference between ARM and Intel. So we see that not the same strategies work the same, but this strategy worked best than the previous one in both CPUs. Okay. And this matched the operation counts. So it's not just like hacking away, measuring, hoping it's good. We did operation counts before. Mm. So we would know what optimum value of W would be, and that matched the experiments. Right. This is all in the paper, of course. It's on ePrint. Numbers for Intel. Intel have lower cycles, of course, because the CPUs have been around longer, have faster arithmetic, essentially. So we have 4Q as the previous record holder here. This is our speed record from 14, the chess paper I mentioned before. This was the follow-up from 16, we were in 38,000 cycles. So that was the previous record. We held the previous record already. So on Haswell, so comparing the new strategies with the previous Haswell numbers, we see that with W equals 3 again, we have just a slight speed up. The speed up is smaller than the previous one because, again, it's trade-offs in architectures. And if you look at the Kaby Lake numbers, we couldn't find exactly the same CPU we benchmarked in 2016. So we got the closest possible CPU and we ran the same code for fairness. Just running the old code in the new CPU got us 2,000 cycles less. With this new strategy, we still beat by 700 cycles. Very small difference, but still a difference. But the speedups on ARM are more noticeable. Exactly because ARM has a higher penalty by reading tables. So making the table shorter makes more of a difference there. So the code is online, is on GitHub, both the ARM, the Intel implementations, and the Sage scripts to compute operation counts, such that this is reproducible. We want to still continue working on this. Some follow-up work is to use bigger vector instructions like AVX512 to accelerate this further. Use the idea for prime curves, which have endomorphisms too. This 2D table idea should apply there as well. And I also want to do a more careful benchmark with latest machines. If you pick the latest Ice Lake I could get from Amazon, assuming that measuring cycles there is consistent, which I really don't know, we got 24,000 cycles. That's very, very small. To give one idea, I benchmarked context switch in a thread in that same machine, and that was 8,000 cycles. So we can compute the scalar multiplication in the cost of just switching from threads 3 times. That's super, super efficient. And if you look at the history, the earlier papers in 2000s would spend more than 1 million cycles to do a scalar multiplication. And every now and then someone finds a nice idea to make this faster. This is the Curve 25519 paper. This is the GLS paper. This is, I don't remember what this is. This is our paper on chess. And so, this should be our paper on chess, yeah. I don't remember what this one is. Maybe it's this is the 4Q paper. This is a bunch of papers, of course, proposing optimizations, and the latest record is here. So we went from more than 1 million cycles to just 24,000 cycles in less than 2 decades, or more than 2 decades, of course, 22 years. And this I'm counting in cycles. I'm not counting, of course, in clock time, because that would not be fair due to frequency differences, right? Yeah.
So a very stupid question. How many cycles does a SHA-3 evaluation, a compression function, cost?
I don't remember.
Anyone
I
remember?
don't really.
7, 8 cycles.
But per
Per
byte?
byte?
Per byte, so it would be,
Yes, per byte. Maybe less now. Maybe less now.
But-
During the competition, they were around 10. Improve it a little bit.
so we're talking hundreds of cycles for a full compression function evaluation.
Well, one invocation, meaning one.
Yeah, no, but I'm just thinking how
Trying to
much
relate,
does
yeah.
the hash functions that I stuff into any construction I make cost compared to this exponentiation?
This is still more expensive, yeah.
Yeah, it's more
100,
expensive, but it's not
100.
like if I had
Insanely more
lots of,
expensive, yeah.
it's not insane anymore,
No, yeah.
like it was on the left-hand side.
Yeah.
Still 100 maybe ratio.
Yeah, 2 orders of magnitude.
Yeah, 2 orders of magnitude.
Yeah,
Yeah.
but still, okay.
Of course, the ratio, I shouldn't say that. I don't know if hashing got faster by the same rate in the same time. Maybe not. I really don't know.
They implemented SHA-2 in hardware.
Yeah, true.
So
And we're relying on special instructions here too, so it's only fair. Yeah. So now, as I promised, any other questions before we quickly move to lattices? I'll just be very brief because I'm out of time anyways. No other questions. But no one cares about any of this, right? We need to move to post-quantum crypto, dialectic die. So how much of this applies still to lattices? Not a lot, but some building blocks, of course, are shared, right? In lattices, you work on these rings, so some special values of n there if you want the most efficient instantiations, but you have a ring over FQ. The big difference is you have rings with 256 degree or higher, but smaller Q. That's the trade-off. You have larger degrees, but smaller coefficients in comparison, which favors vectorization, multiplying or doing arithmetic over many coefficients at the same time. And I stole this from one of Peter Schwab's slides. It says that post-quantum is about vectorization, right? Instead of the 64-bit multipliers that are too large and do one multiplication at a time, now it's doing many smaller multiplications at the same time. The fundamental operation, of course, is not scalar multiplication anymore. It's something different. It's matrix vector multiplications of that form, or A is a large matrix multiplied by V, and you add some noise E sample from some noise distribution. That's the core of like chems and signatures, shuffles and BGV, homomorphic encryption. That's what you find everywhere. What can you do in terms of optimizations? One thing is picking Q to be small and such that the reduction modulo P is fast. You need to reduce modulo Q for arithmetic in these rings. And even though Q is smaller than a word, you cannot just use the integer division instruction to reduce modulo Q, because it runs in variable time. So I actually need to find a way to reduce by Q that's sufficient, vectorizable, and runs in constant time. So picking Q can be very important. In terms of polynomial multiplication, that's exactly what you need for that matrix vector multiplication there, right? The matrix is a matrix of elements in this ring. You can both use in general Karatsuba, as I just showed for the binary field arithmetic, or Tom Cook for splittings in more than 2 divide and conquer steps. But the real king performance-wise is when you have special choices of N and Q that give you the NTT. The NTT is the discrete version or the number theoretic version of the FFT that you, as in the FFT, you pay n log n for degree n to convert to the domain, and then you can do multiplications coefficient-wise, so they run in linear time instead of quadratic or subquadratic as we had with Karatsuba and the fields I showed before. And what's funny about post-quantum crypto, or lattice-based crypto in particular, it's not true for exogenous, is that this is so fast that what dominates the symmetric parts. So for example, in many schemes, this matrix A will be large and will be the same, will be fixed. So you expand it from a smaller seed. So you need a shake function, some Chatry function to expand smaller seed into large A. That will actually dominate the polynomial arithmetic. So the polynomial arithmetic is not that much of a problem anymore. But these are the parameters that are most efficient, and all the standardized candidates are entity friendly, I think, the ones that are in their last round. You still find binary fields, I think, on Saber, where Q is a binary field. So you still find candidates out there, although not finalists, that use the techniques we had before. In terms of implementation security, what worries me, we're using these vector instructions to do a lot of smaller integer multiplications in parallel, but are they constant time? We always thought they were, because who would not do that? But Intel a few months ago published a list of what instructions they guarantee to be, it's not a list of instructions they guarantee to be constant time, it's the list of instructions that they have high confidence that they don't run in constant time under some configurations. And the vector instructions are all there. So then we don't know. There are bits you can set in the CPU to say, oh, don't make this data dependent and so on, that may alleviate that, but it's unclear. But that's something that's people are playing right now with micro benchmarking to figure out what corner cases trigger these optimizations and how much that changes. Other problems that I see, or this literature, of course, pointing at is the distributions where the error in the previous slide is small e sampled from. It can be really hard to sample from some of them in constant time as well, especially Gaussians. There are several schemes that use discrete Gaussians, rounded Gaussians, and you need large tables. It's tricky to do this in constant time. That's why the standardized schemes, I think, do binomial or uniform only. That's simpler to sample. Rejection sampling for signatures is a problem. We were discussing this at the beginning. In some signature schemes, you try to compute the signature multiple times, and then you throw away the ones that you throw away the ones that wouldn't satisfy some bound, right? Some norm bound. So of course, if you do that, you cannot preserve state from one to the other. That might leak information about the secret key. There is a very nice paper attacking the Bliss lattice-based signature scheme that essentially does that. It has some correlation between the rejection sampling steps that allows you to recover, allows an attacker to recover the signing key with a sidechain attack. Other papers deal with the Fujisaki Okamoto transform to give CCA security by doing fault attacks and making the testing or the checks in the fault transform pass, even though that's not the case. And the very extreme case, thinking of sidechain attacks, there is a very nice paper doing code boot attacks in which you pick a version of RAM memory that's frozen, right, and try to recover keys from there. And they figure out that if you represent keys, for example, in the entity domain, that adds redundancy and make key recovery of noisy bit strings actually simpler or more practical in several instances. But code boot attacks is only important for stuff like disk encryption, right, or something like that. It's not a primitive. It doesn't impact primitives we use that much. How do you defend against these things? Again, the same ideas I had before, right? It's constant time implementation, mixing randomness as what we call masking, which can be quite efficient in some of these schemes, and so on. So if you want to play with implementations of lattice-based crypto, there is plenty of reference code from the candidates themselves that were submitted as part of the NIST process. There is also a very nice library called Latigo in Go that you can pick up quite fast and has multiple schemes and homomorphic encryption implemented, and it's quite pleasant to use. And I think that's all I had. Thank you very much. We may have still some time for questions.